Okay, we're going to try this again. Today we're going to be talking about thermochemistry. Sorry it's late. Been having a little technical difficulty getting everybody quiet. Hopefully it's quiet enough. There's a little background noise, so hopefully though with the headphones it detains that or lessens that about a little bit. So we're going to start talking about energy. Energy is defined as the ability to do work or to transfer heat. Work is a physics term that means moving an object with a force a certain distance. It's defined by the formula W is equal to F times D, where W, little w, is work, F is force, and D is distance. And we have units of newtons, which is the unit of force, and distance, which is meters. But that also, in terms of units, breaks down into kilograms times meter squared per second squared, because a newton is a kilogram times meter per second squared. That's a newton, right? So that all equals joules, which should be somewhat familiar, sorry. Heat, on the other hand, is something a little different. It's the ability to change the temperature of a substance. It has units of joules, don't have to be translated. Types of energy, there's kinetic energy. Kinetic energy is known as the energy of motion, and for us, in chemical terms, that can be translational motion, that's sliding back and forth, translational motion. Okay, rotational motion, that's going round and around and around. Vibrational motion, just vibrating. And kinetic energy is proportional. This little symbol right here in the center means proportional to temperature of a substance. Kinetic energy is equal to 1/2 mv squared. That's the mass and velocity. So we knew from our gas laws issue that we had to know the mass of a particle and the velocity of a particle to find its kinetic energy. We also understood that if everything was at the same temperature, then the velocity was really close to the same. So the only thing that was different about particles was the mass. So that's going to probably come into play a little bit later for us too. So mass and velocity of particles matter to us. Potential energy, on the other hand, is energy by virtue of a position. So that's like when you have a big hill and you have a rock at the top of the hill. That rock has a huge amount of potential energy because if it rolls over the hill, it will convert that potential energy into kinetic energy by virtue of rolling. But because it's placed above a flat valley area, it has potential energy. Okay, in chemistry, that's usually about the energy stored between the bonds. So we have atoms that come together and join. And this bond area right here is an area of stored energy. So when bonded atoms are separated, so when we try to separate these two atoms, the potential energy has to be raised because you have to add energy to overcome the attractive forces between here. So there's an attraction here that's holding these electrons and these atoms together. And so you've got attractions and repulsions both going on at the same time between the nucleus and the shared electrons. There's lots going on here. But that means that we have to add energy to break a bond, which is a little strange to some of you. Okay, when atoms bond, the Coulombic attraction is being released. So we have to release some of this attraction, therefore release some energy, so subsequently we have a lower potential energy. So when atoms are bonded, they have a higher potential energy. When they bond together, or when they're trying to be separate, they have a higher potential energy. When they're being bonded, they have a lower potential energy. And that goes into this idea of ATP creation in biology, and this whole bond breaking gives you energy. It's not the truth. It requires energy to break a bond. Making a bond gives off energy. So I want you to be aware of that. So breaking a bond means you need energy. So it requires energy to be put in to do that. Making a bond releases energy. And this is one of the things that most biologists and chemists really disagree on, because everybody's taught that, oh, the energy releasing process of ATP, there's a process in there, but the chemical reaction involves a bunch of breaking and making, and the overall resultant product is a big greater release of energy than need of energy. So we'll talk a little bit more about that later. Okay, energy distribution. So when we look at this, we can see 4 different views. So here's view 1 right here, where we have the two things separated. Notice the potential energy, very little potential energy. And as they begin coming closer in view 2, as they begin coming closer and they're attracting to one another, notice the amount of potential energy increase that goes up right here. So if we look straight down, we see lots more potential energy than we saw right over here. Okay? And then finally, if we look at where they're coming together at their best bond, we can see we've maximized the potential energy. So we have maximum amount of potential energy right in here where 3 is, and that's at the bond length between H2, the actual bond length. And then if we try to force them to get closer together, you can see very quickly that the potential energy begins to change again until we have increased potential energy, so there is none, and it's negative potential energy. So we have to kind of remember that. So the Boltzmann distribution, which is what this graph is called, is a graphical way to show the energy distribution in a molecule. We are going to come back to Boltzmann a little bit later in discussing how we understand average temperatures and things like that. So we'll come back to that in a minute. Well, actually, in another video. So, thermochemistry is defined as a relationship between a chemical reaction and the energy change involved. So this idea that we have of thermochemistry is really about the energy of chemical reactions. And it's really the changing energy. Therefore, our focus will be on more of the side of transferred in heat, not work. Because, yeah, the work is being done over a very, very small distance, but there's very little work that we can measure out because we've got so much breaking and so much making going on. And so we're going to look at heat transfer more than we're going to look at work. So the law of conservation of energy states that energy is never created or destroyed. This implies that any change in energy of a system must be balanced. That is a really important term. Everything must be balanced by the transfer of energy either into or out of the system, depending on the original direction of the change. That means if I've got energy going out of the system, there has to be something to balance that energy going out of the system. It just can't disappear into nothing. And this is where we get the first law of thermodynamics. So the law of conservation of energy leads us to the first law of thermodynamics, which basically states that energy of the universe is constant. So the energy that existed still exists. It's being transformed and transferred all over the place forever and ever and ever until eternity. Okay? And some of you might disagree with that, but right now, that's the first law of thermodynamics. It's been the first law for a long, long time. So the first thing that we need to talk about in thermochemistry is heat. Heat is defined by the equation Q is equal to M times C times delta T, where this is the mass, this is the specific heat capacity of a substance, and this is the change in temperature. And remember, this is considered a constant, but it's constant for a substance. So it's not constant over everything, it's constant for each different substance. Okay, so two systems with different temperatures that are in contact with one another will exchange that thermal energy. And that quantity of the exchange is called heat. So the transfer of energy in this process flows from a warmer object to a cooler one. Transfers of heat because temperature is different. But remember, temperature is not a measure of energy. It just reflects the motion of particles. So what we're really looking at is how does that energy in terms of heat transfer? And we're looking at temperature to help us understand that transfer. Look, it's not the only thing. Temperature is not the only factor involved in the heat equation. So heat can be transferred between two objects due to temperature differences. A warmer object will make a cooler object warmer. Okay? Doesn't go the other way. So one object loses heat while the other one gains heat. It's what we call a simple handshake of energy. So I touch you, you touch me, my hands are cold, your hands are warm, you're going to pass heat to me and warm me. Okay? This is called negative Q loss is equal to Q gain. So what we're saying is, as these objects are losing and transferring heat, the one that's losing is transferring equal amount of energy that the one is gaining. Okay? And for most situations, that really works, especially if we have really good instruments that we're measuring with and really good apparatus. Okay? So, understand heat units. There are two categories of heat units, SI and standard. We're going to start off talking about SI. The SI is a System International. Those are the things like meters and grams and the things that we all use in science classes. A joule is the SI unit of heat used by most scientists. 4.184 joules of energy are needed to raise 1 gram of water 1 degree Celsius. This is the specific heat capacity of water. And this is the definition of it in the SI system. 4.184 joules are required to raise 1 gram of water 1 degree Celsius. That's basically what specific heat really means. And 1 kilojoule, kJ, is equal to 1,000 joules. So this is just the kings have dungeons under dark castle moats, where the joule is the under and the K is here. And so if we go here, we go 1, 2, 3, which means we have 1,000 joules. Okay, we see this very often in European labels. So if you look at this label I believe is Germanic, something like that, Dutch maybe. But you will notice that its energy up here where we see energy, notice it's in kilojoules. It also has something called kilocalories next to that. We're going to talk about that in just a second. So we can see that different places have different ways of measuring things, but in Europe they usually use the SI system, even on their labeling. Okay? So, standard, or the American system, is calories, little c calories. Now there's a really big difference. There's a little c calorie, there's a big C calorie, and there are kilocalories. Okay? A little c calorie is the amount of energy required to raise 1 gram of water 1 degree Celsius. It means 1 little c calorie. So that's the specific heat capacity of water in the standard system unit. That's going to come into play in just a few minutes. So 1 kilocalorie is equal to 1,000 little c calories. So we're seeing a very similar thing. But this idea of big C calories really throws us off, because kilocalories are the same as big C calories. And these are the ones that are on our food label. So when we look at a food label that we have, we see that there are 230 calories, and you notice there's a big C, so that's 230 kilocalories, which is why on the other label we saw kilocalories instead of just big C calories. They really try to make a distinction. So how do we relate these together? Well, there's a hodgepodge of units, and we use all of them, unfortunately. But like most things, we can narrow them down with conversion factors. So we can see 1 kilocalorie, or big C calorie, is equal to 1,000 calories, little c calories, which is equal to 4,184 joules, which is equal to 4.184 kilojoules. Okay? So these are all conversions. That means they have an infinite number of significant figures, and we don't have to worry about sig figs on that. Okay? So heat and work. So if heat is being transferred, work can be done. And that means there's a force acting over distance, and we talked about this a little bit. So remember, there's something called the Coulombic force. Remember the Coulombic force? The force is equal to some constant times the charge on one times the charge on another over the distance squared, right? Well, this is a force. This describes the force of even small particles. So if we do that, even movements of atoms over very small distance provide some work. But we live in chemistry world. And the only work that we're going to be working with, work that we can actually measure using our tools, is going to be PV work, pressure volume work. Okay? And this is only applied to gases. So that means in our world, work will really not be considered very much, but we need to understand how it interplays. We will be focused on heat more than work. Okay? So PV work, blowing up a balloon. So this is W is equal to negative P delta V. That means delta V is final volume minus the initial volume, as always. Pressure is always the outside pressure. It's given to you. So if gas is expanding, work is required to expand that gas. So work flows out. Therefore, work would be negative. On the other thing, if gas is compressing, work is flowing in. Therefore, it would be positive. So you have to remember that. So compression means that work is positive, okay? But these have goofy units. They have units of atmosphere liters or liter atmosphere. Sometimes you see them like this. It doesn't really matter. Same thing, okay? How do we compare that to Q? Well, 1 liter atmosphere is equal to 101.3 joules. So, system versus surroundings. What are we looking at when we have heat being transferred? Well, we're looking at this idea of a system. That is, for us, the chemical reaction versus surrounding. everything around it. So when we look at this square, we define this square as the system. And that means everything around the square is the surroundings. And we have to be really clear on defining what that is. So we kind of stick to this idea of whatever the reaction is the system, and everything around it is the surroundings. Okay? So energy flows in two ways. Exothermic energy flows out of the system into the surroundings. Endothermic energy flows into the system from the surroundings. So characteristics of an exothermic reaction. Product bonds are stronger. Why are product bonds stronger? Well, they have more potential energy. More potential energy means I had to add that potential energy, and those bonds are closer. So heat is found on the product side. Because the potential energy is bigger in the products, that means it had to gain energy in order to get there. It had to give off the energy in order to get there, to get more potential energy. Some kinetic energy had to be given off. So that means this thing feels hot to the touch. So the heat value is considered to be negative, and this is a really important thing. So exothermic reactions are negative reactions. When we have changes in heat, they're negative. Okay, so this is an exothermic reaction. Here we see reactants, and we see products, and we see how the reaction is occurring, right? And we see that this between the reactants and the products, this value is called enthalpy. And enthalpy is how we measure heat in a reaction. And notice it's products minus reactants, the PE of the products minus PE of the reactants. I want to point out this activated complex, also known as the transition state. I think you're going to see that on your guide. Transition state, what that basically means is that there's something here that's formed between reactants and products that has to be formed in order for products to be created. And that's called the activated complex or the transition state. And it's usually some combination of what's going on that will then allow the reaction to proceed on. The energy that it takes to get from the reactants to the activated complex is known as the activation energy. That's the amount of energy that has to be added in order for the reaction to happen. So some reactions don't occur because the activation energy is too great. Okay, endothermic reaction has different characteristics. Products have higher potential energy, but product bonds are weaker. Not much energy is needed to reform the reactants, and we'll see that in just a little bit. Okay, heat is found on the reactant side, and it's taken from the surroundings, so it means it's going to feel cold. The container that everything is in is going to feel cold. So when it feels warm, that's exo. When it feels cold, it's endo. And that means that it is going to have a positive delta H. So delta H, or the enthalpy change, is going to be positive. So here we go. Here are reactants, lower potential energy, products, higher potential energy. Okay, and we see the difference. So the difference between those two, well, if this is higher and this is lower, we're going to have a positive delta H. Okay, same thing applies. We still have to have an activated complex, but if you look at the difference in energy from the products to the activated complex and the difference in energy from the reactants to the activated complex, a lot more activation energy has to be applied. So a lot of endothermic reactions don't happen very often. They're not common. They happen, but they're not common because of that. Okay? Because of the fact that the activation energy to go backwards is lower than the activation energy to go forward. Okay? So internal energy is the sum of the potential energy and the kinetic energy of all the particles. So delta E is the change in internal energy is equal to Q plus W. That's heat plus work. So if we have the situation where Q is negative and W is negative, then delta E is going to be negative. That makes sense. Okay? If Q is positive going in and W is positive because the surroundings are doing work in the system, then delta E is going to be positive. In this situation, look at the magnitude of the difference. Okay? Q is positive. So Q is positive plus a negative W. But look how small W is. So overall, in this particular situation, you're going to have a positive delta E2. Now, if it's opposite, if this is smaller and this is bigger, then it changes, and we see that. So internal energy does reflect direction of the sign. So when heat is absorbed into the system by the system, it's positive internal energy. When heat is released by the system, it's negative internal energy. Okay, and that kind of goes along with what we're talking about. This would be exo, and this would be endo. Okay, heat being released by the system as it's doing what it's doing, or heat being absorbed by the system as it's doing what it's doing. So the value or number reflects the magnitude or the amount of the heat given off. So exercise 1, it says calculate delta E for a system undergoing an endothermic process in which 1.56 or 15.6 kilojoules of heat flows where 1.4 kilojoules of work is done on the system. So it's really important that we take a step back for just a second. Remember what it said? Heat absorbed by the system, heat released by the system. Okay, and we have to go back to our Q and W. So we know it's endothermic, which means that delta E is equal to Q plus W. So Q here is the 15.6, and it's endothermic, so it's going to be positive, 15.6 kilojoules, okay, plus the work is being done on the system, so that is also positive. So we get 17.0 kilojoules for our answer. Pretty simple. Okay, calculate the work associated with the expansion of a gas from 46 liters to 64 liters at a constant external pressure of 15 atmospheres. Well, again, we just go back to equations that we just learned. Work is equal to negative P delta V. So we have negative 15 atmospheres times 64 liters minus 46 liters. And we get negative 15 atmospheres times 18 liters, and we get an answer of, let me look, I have it all written down, so I made sure that I knew what I was doing, had all my answers. Sorry, I've just been going. All right, so that gives us negative 270 atmosphere liters or liter atmospheres. It doesn't really matter how you write that. But it's negative. Why? Because I've got a negative sign right there. So work is being done to expand a gas, so the heat should be negative or the work should be negative. Right? Expansion, negative work. All right, finally, a balloon is being inflated to its full extent by heating the air inside. The final stages of this process, the volume of the balloon changes from 4.0 times 10 to the 6th liters to 4.50 times 10 to the 6th liters by the addition of 1.3 times 10 to the 8th joules of energy as heat. Okay, assuming that the balloon expands against constant pressure of 1 atmosphere, calculate the delta E for the process, convert between. So we're given our conversion factor. So let's start. So we have to start with our work. So work is equal to negative delta PV. So we start plugging in numbers, negative 1.0 atmospheres times 4.5 times 10 to the 6th liters minus 4.00 times 10 to the 6th liters, and we get negative 5 times 10 to the 5th liter atmospheres, which we have to then change by taking 101.3 joules over 1 liter atmosphere, and we end up getting negative 5.065 joules of energy. Oh, I'm sorry, times 10 to the 7th joules of energy. Then we plug that into the delta E equation. Delta E is equal to Q plus W. Okay, Q plus W. Sorry about the break there. So delta E, the internal energy, is equal to Q plus W. So we go back to the problem and we find that the Q is being put into the system. So that means it's positive. And we can see that the W is negative. So we're adding negative 5.065 times 10 to the 7th joules. And we add all that together and we end up with 7.9 times 10 to the 7th joules of energy. Okay? That's the answer to that question. So I'm going to go ahead and stop right there for right now.